In this section, you will be finding polynomial functions that can be used to approximate transcendental functions. If p of x is a polynomial function used to approximate some other function f of x, they must contain the same point with some x value c. That means p of c is equal to f of c. To be a better approximation, they should have the same slope at that point. That means p prime of c is equal to f prime of c. For even greater accuracy, p prime prime of c should equal f prime prime of c, and so on. Putting this together gives us the Taylor polynomial expansion. If f of x has derivatives of all orders, it can be approximated by the polynomial function shown. This is called an nth degree or nth order Taylor polynomial centered at c or expanded about c. When the center is at c equals 0, the Taylor polynomial is called a Maclaurin polynomial, which can be written as such. These are extremely important formulas and must be memorized for the BC exam. For example 1, we're going to use the definition of a Maclaurin polynomial to find the 5th degree Maclaurin polynomial for f of x equals e to the x. Go ahead and derive. Oh wait, the derivative of e to the x is e to the x. If we're centering at c equals 0, we need to find f of 0, f prime of 0, f prime prime of 0, and so on. That would be e to the 0 for all of these, which is 1. Because this is a 5th degree polynomial, I will write it as p sub 5 of x. Following our formula for a Maclaurin polynomial, we'll begin by putting f of 0, then adding f prime of 0 times x plus f prime prime of 0 times x squared over 2 factorial plus f prime prime prime, the third derivative of 0, times x cubed over 3 factorial. Ours is 4th degree, so the next one would be the 4th derivative at 0 times x to the 4 over 4 factorial. And our final term will be the coefficient, which is 1, times x to the 5 over 5 factorial. This is the 5th degree Maclaurin polynomial for e to the x. It's already simplified, but if you wanted to rewrite it without all those ones, this polynomial is a good approximation for f of x equals e to the x. By extending the pattern into an infinite series, it becomes exactly correct instead of an approximation. So our series would look exactly like our polynomial, except we're going to show the nth term, and don't forget a plus dot dot dot. This would be x to the n over n factorial, and n would equal 0 for that first term to be 1. Plus dot dot dot. Now we have a Taylor series. This is also known as a Maclaurin series because it is a Taylor series that centers at 0. The general form of Taylor and Maclaurin polynomials can be extended to Taylor and Maclaurin series. These formulas allow us to form a power series for functions that cannot be written as geometric power series. So in yesterday's lesson, we turned a rational function into a power series or a series with an x in it. But these transcendental functions cannot easily be translated using the sum of a convergent geometric series formula. For these transcendental functions, we use Taylor and Maclaurin series to allow us to form a power series. The series formula for Taylor and Maclaurin series is just like the polynomial formula, but you show an nth term and you got the plus dot 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 to show that it is infinite. Example 2, use the definition of a Taylor polynomial to find the 4th order Taylor polynomial and the Taylor series for f of x equals cosine x centered at c equals pi. This is not Maclaurin because we are not centered at 0. The derivative of cosine x is negative sine x. Derivative of negative sine x is negative cosine x. Then we have negative sine x, so sine x. The derivative of sine x is cosine x, and the derivatives would cycle through these 4 if we continued. Now let's evaluate each of those at pi. Cosine of pi is negative 1. Sine of pi is 0, negative 0 is 0. Negative cosine of pi would be negative 1, so positive 1. Sine of pi is 0. Cosine of pi is negative 1. Our Taylor polynomial will be the same as the Taylor series, but it will not be infinite. We will stop at the 4th degree term. F of c is negative 1. F prime of c is 0. Speaking of, c is pi, remember. All right, look at that. Well, we do have a couple terms that multiply by 0, so we can simplify that polynomial. All right, there is our fourth degree, or fourth order, Taylor polynomial for cosine x centered at c equals pi. Our series will have the same terms, plus dot 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 plus our general term. Our general term is the nth derivative at c, remember c is pi, times x minus pi to the n all over n factorial. Don't forget a plus dot 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 at the end. And there is our polynomial and our series. For example 3, we're going to use the Taylor polynomial from example 2 to approximate cosine of 3. Our polynomial was -1 plus x minus pi, and now x, we're plugging in 3. Use a calculator, and that gives you -0.9899924, and so on. What happens if you plug in cosine 3 just directly into the calculator? If you do that on the calculator, you get 0.998629. Pretty good. For example 4, we're going to use the definition of a Maclaurin series to find the Maclaurin series for sine x. Remember, Maclaurin is a Taylor series centered at c equals 0. Begin by deriving. Now evaluate. Let's fill in our series. Our nth term would be the nth derivative at 0 times x to the n over n factorial. Don't forget your plus dot dot dot. And now simplify that series. And here is the Maclaurin power series for sine x. For our final example, find a power series for f of x centered at c equals 1 if f of 1 is 2 and the nth derivative of f at 1 is n factorial. Here's our given information. Now, the first derivative at 1 is going to be 1 factorial. The second derivative at 1 is going to be 2 factorial because it is the second derivative. The third derivative at 1 will be 3 factorial. I think going to the third derivative is sufficient, and then we'll also put in that nth term because this is a series, not a polynomial. Here's our formula for a Taylor series, and let's go ahead and fill in those terms. We can simplify by reducing the factorials and also distributing this 1 and combining like terms with the 2. And there's our power series.